Mr. over here. And I just wanted to go over this warm-up with you guys. So I hope you looked at this and you thought back to last week when we talked about this big F function that's defined like this. And you thought, oh, big F is the accumulator. It's the accumulator of the area under this graph here, which is the little f. Okay, so how do you evaluate f of different x values? By finding the area from 0 to whatever x value you're plugging in under little f. It's the accumulator. It measures the accumulation of the area under little f. Okay, so using that logic, well, the accumulation of the area from 0 to 0, well, it's just 0. From 0 to 2, we've accumulated positive 20 area. From 0 to 4, we have our positive 20, but we have our negative 18.75, so our accumulation of our area is 1.25. Okay? And you go ahead and fill in the rest of this out like this. The only thing that's got a little tricky is over here for this chunk to figure out that height. You might have had to write a little equation maybe. Yeah, just to make sure you're figuring out the right height there, excuse me. Okay. Once you do that, part B is saying, where does f of x have its minimum? Okay. Now, there's a couple of ways to think about this. First, you can totally sketch the graph for f of x. We have these points. We can totally plot big f of x and see where it has its minimum. But the question asks us to justify this with an explanation involving derivatives. So this is the key idea. When you see the accumulator function, the integral function, you need to remember this. This is fundamental theorem of calculus part 2. FTC, that second part. When you have the accumulator function and you do the derivative of it, the derivative and the integral cancel each other out because they're inverse operations, and you're just left with the inside part. In other words, the derivative of this, it's just the inside part. The derivative of big F is little f. So then if you think about it that way, when does a function have a minimum? Well, if you think about derivative speak, it's when it goes from decreasing to increasing is where you have a relative minimum. It's where the derivative, so now this is little f, which is the derivative of big F, goes from negative to positive, decreasing to increasing. Big F is going from decreasing to increasing because the little f is going from negative to positive, and that happens at x equals 6. Okay. It'd be nice, since it's kind of asking you for... Actually, I take that back. It'd be nice because it's asking you for a minimum. It means the absolute minimum. It'd be nice to also compare big F of 6 to big F of the endpoints of the interval. So you should compare big F of 6 to big F of 0 to big F of 12, just because this justification definitely says that at x equals 6 we have a relative minimum, but it'd be kind of cool to make sure that that relative minimum was an absolute minimum. Okay, and if you go back to our table, f of 6 is negative 4.25, f of 0 is 0, f of 12 is 21.75. So that relative min that we justified using the first derivative test is an absolute min because its y value is literally lower than the y values at the endpoints. Similar logic for C. When does f have its maximum? Now you can think about this in terms of the accumulator function itself and kind of figure this out. I want to do the derivative explanation, but I just want to kind of walk through this with you to make sure we're cool. If you think about the accumulator and when it has its maximum, well, I'm getting bigger, I'm getting bigger, I'm getting bigger, I'm getting bigger, I'm getting bigger. Maybe this is the maximum, because then I'm getting smaller, 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 because I'm accumulating negative area. But then I'm getting bigger, 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 bigger. So then the question is really, am I biggest right here? after I've got some positive, negative, positive, or am I biggest right here? Those are kind of the two ones that, to me, understanding the accumulator function, I'm thinking, when does big F have its maximum? Those are what I'm thinking about. But if I'm going to use calculus, I'm going to use candidates test. I'm going to test the endpoints, compare them to the critical numbers. Okay. So again, what we're doing here is saying that the derivative of big F is little f. I have a relative max at 2 because my derivative goes from positive to negative. Increase and decrease, that's a relative max. Okay. So at x equals 2, I have a relative max. Here's that justification using those intervals. It's important that you use this interval notation that Lemke used here. Look at that line, make sure you have that line on your paper. But then she's comparing it to the endpoints, which you really should have done in B as well. That is because just because something is a relative max doesn't mean it's the absolute max. One of the endpoints could be the max. And in this case, the endpoint actually is the max. So 2 is a relative max. Look at the graph of little f, or big F. But the endpoint is actually higher. Okay? So you need to actually compare the critical numbers, the relative max, to the endpoints. And literally, the endpoint has a bigger y value than the relative max. So the absolute max happens at x equals 12. This is called the extreme value theorem. Lemke and the AP sometimes call it candidates test. The candidates for an absolute max are the endpoints and any relative maxes. That's why it's called candidates test. Yeah. I know this is a hard question. That's why I just wanted to do this opener with it. Thanks for listening, guys.